So, this section should hopefully be no big deal. This is something that you most likely, if I remember correctly, did in BC Calc. Direction fields. Maybe you call them slope fields. Okay? Don't lie. You didn't do slope fields?
No, I did. That was just the worst unit there was.
Oh, okay. You didn't want to do. Okay. Well, see, here's the good news. We've pretty much done something similar to this year in Calc 3, right? We called them what? Vector fields. Okay, the only difference is going to be that instead of having at each point a specific vector that's a certain size and a certain direction, here all we're going to do and this is what you did last year, is just draw tiny little segments with the correct slope at each point. Okay? And this is going to paint a picture as far as like what the solution for the differential equation is going to have to look like. Did you guys do that at all last year? Okay. So, for example, let's say we have the differential equation y prime equals y. Okay? This means that the slopes of the tangent lines to the solution curve are given by f of xy equals y. Okay, this over here does not have to be necessarily just in terms of y. It could be dy dx equals x squared plus y, or it could be a function in two variables. So we're going to call that f of xy. Okay? And if we kind of get an idea of what's going on, since the slopes are just going to be exactly the y-coordinate, right, this is a pretty easy direction field to sketch. Along y equals 0, you just have flat segments. And as you go up, you get slopes of 1. And the steeper or the higher you go, the steeper the segments are going to be. And now, as we go down, same idea, except now we have negative slopes. If we go down to where y is equal to negative 2 or negative 3, steeper, more negative, you get the idea. Okay, so here's y equals 0. This was y equals 1 right here. Maybe I'll do those. Y equals 2, y equals negative 1, y equals negative 2. Okay? And now, we can go ahead and talk about this now, but this is one of the big ideas in this section. From a direction field, if you're given a point, like an initial condition, let's say that we're looking for a solution to this, but for example, so that it goes through 0, 1. Okay? Well, here's 0, 1, right? So this point needs to be part of the solution curve. And as I go right, according to my direction field, what needs to happen? This needs to increase, right? This is going to get flatter here. It looks like it's going to approach 0, not go through that. And so this would be a sketch of a solution curve to this differential equation. By the way, you should know what solution curve that is. E to the x, right? Y prime equals y, e to the x solves that. And specifically, if it goes through 0, 1, there you go. Okay? So that would be one example. Okay? In general, maybe a little bit more. Each little segment is called a lineal element. So you'll see the text throw that around. That's what they're talking about. Okay? And now, in general, any member of f of xy equals c is called an isocline, and what that means is that it's a curve along which slopes of tangents are equal. So in this case, we actually drew 5 isoclines up here, mainly y equals 2, 1, 0, negative 1. So they're not quite curves here, but these blue horizontal lines would be 5 separate isoclines. Along these 5 horizontal lines, the slopes are the same. That's what that means. Okay? In this case, they were lines, but they certainly could be curves. As c varies, so as we vary this constant up here, we get a collection of isoclines along which lineal elements are constructed. Okay, all of this together is called a direction field. You've probably referred to it as a slope field in the past. And we'll also call it, but not often, a lineal element field. Oops, I just wrote element twice. Lineal element field. Okay, and this will help us find a solution curve through a specific point. So this is basically the process that we just illustrated up here, in case you forgot what we did when you're looking back at this later. Okay? Oh, specific point. All right. So here, why don't you guys take a look at this example using the knowledge that we reviewed here or learned. Determine the isoclines for the differential equation dy dx equals x squared plus y squared. Okay, so why don't you sketch a few of them? Okay, remember, look at what you're being asked. You're not sketching the direction field yet. I mean, we're going to get there. First, let's find the isoclines. What shape should we be having here? Yeah, circles. So if we just set this equal to some constants, right? Some nice ones. We just get that we get circles as we vary this. Okay, so if we have, here's where this constant equals 1, right? We get a circle of radius 2 when the constant is equal to 4. Circle of radius 3 when the constant is equal to 9, right? So these would be 3 isoclines for this differential equation, right? Now, you guys know that each one of these represents exactly where the slopes are identical, right? So along this tiny circle with radius 1, if we were to draw a direction field, we would draw segments that all have a slope of 1. Does that make sense? And then as we go further out, the slopes get steeper. Okay? So just be careful with the homework. Like, depending on what they ask, you don't have to necessarily draw a direction field for every single question. They might just say, find the isoclines or things of that sort. Okay? Let's try an example here where we're doing a little bit more. Sketch a direction field for dy dx equals x over y. Yeah. Okay, I'd probably start with some very basic assumptions here, like if y equals 0, what's the slope? So that means that along our x-axis we have vertical. You guys did some of those too, right? Vertical segments. I'll use green for the... Excuse me. Thank you. If x equals 0, so that's along the y-axis, what slope do we have? Zero. Good. Well, now it just looks like an xy axis with tick marks. But that's actually part of the direction field, right? We can do some basic ones like, let's see, some nice slopes. So I'm kind of approaching this a little different than the other ones. Another nice slope here would be like maybe 1. So what would produce a slope of 1 here? Y equals x. Very good. So if y equals x, slope is 1. So then that means that along the line y equals x, we have something that looks like that. We can kind of go the other way, and if we do negative x, now our slope's negative 1, right? Hi.
Alex and Greg.
Yeah.
They're supposed to be in 110 today, I guess.
They're supposed to what?
I don't know if they're supposed to be in 110 or just go see that.
Alex and Greg? Oh, is it because they were absent, maybe?
You're excused from.
They were on a field trip. They might not have been excused here.
Okay.
And I was gone. I usually don't mark them absent if I know they're on a field trip, so that could have been why.
Okay. Can they go down and see her
Yeah.
after they're done with what they're doing?
Yeah, you guys can go to where should they?
110.
110. In a few minutes, we'll clear it
Okay.
up.
Okay.
All right, thanks. Okay. So, continuing. Let's get some other nice slopes here. So, I mean, if we do something like maybe a slope of 2, we would say like maybe y equals 1/2 x, since these are inversely related, right? So along y equals 1/2 x, I think I'm thinking about that, right? 1/2 x is canceled, slope is 2. Yes, so along y equals 1/2 x, now we have slope of 2. If we can go the other way, okay, and as you kind of start to get more of these, you're going to start to see what kind of shapes we're going to get here. Okay, if we do y equals 2x, now along a steeper line, the linear elements, or the lineal elements rather, get a little flatter. So along y equals 2x, here the slope is 2. If we have y equals 2x, slope is 1/2. Okay, so flatter. Same thing down here. We can go the other way too. And I mean, it's a good enough sketch. At this point, if you were given a point, you could kind of see that we're going to have probably like a hyperbola sort of solution set, depending on.
They're okay, I cleared it
Oh,
all.
all right. Thank you. So this is a decent. I mean, the ones that are more tedious, as long as you get a nice picture as far as what's happening, that's good enough. Okay. So maybe, I don't know. Here is one possible solution curve, right? If we were asked for one. Okay. Let's do one more. Why don't you guys do this one on your own? So do the whole thing. Approximate a solution curve for dy dx equals x squared plus y squared. So we've already done part of this one. But now I'm giving you the initial condition, y of 0 equals 1. already had the isoclines for this, right? So for this one, instead of saying, well, here the slope is this, here the slope is that, we have curves where the slopes are certain things, right?
It's a good solution curve.
Almost caught it. Okay, so some of you just kind of sketched the direction field a little bit. That's fine. And still got a decent picture. Since we already drew these, right? Here's where the slopes were 1. Here's where the slopes were, 4? Not a very accurate slope field or direction field. And then they get steeper, right? So if we're going through 0, 1, this point needs to be part of the curve, right? And as we go to the right, it looks like we increase, right? And as we go this way, we decrease, but then we start to decrease a little quicker. So maybe, I don't know, something like that. Make sense? Okay, that's it for 9-1. Any questions? All right, so